So in section 11.3, you're going to be performing what's called the Kruskal-Wallis test. Now this is going to be the non-parametric equivalent to the analysis of variance that we did back in chapter 10, because this is a non-parametric test that we will use to test for a difference between 3 or more independent populations. So in the previous section, we had our Wilcoxon test, and those allowed us to test for a difference between 2 groups. The Kruskal-Wallis test will be used when we have 3 or more groups, and we want to test for a difference. Now, as far as the setup of the test goes, much like the other test here, the null hypothesis will always state that there is no difference between the populations. The alternative will state that there is a difference present. Now, just to give you a heads up here, this will sometimes be worded a little bit differently, just depending on how the test is started. So one thing you do want to remember here is when you perform non-parametric test, you can also look at this as testing the value of the median and even comparing the values of the medians. So an alternative way to state this, if there is no difference between the populations, this is the equivalent to stating that all of the medians are the same or equal for the different groups, right? If there's no difference, the medians would be equal to each other. And if there is some difference present, then the opposite of this would be that all of the medians between the different groups are not the same or not equal to each other. So just a different way that can be worded in some cases, so just to watch out for that. Now, much like our other non-parametric test, the Kruskal-Wallis test statistic will be found by looking at the ranks associated with the data. Now, instead of doing all of this by hand and ordering the data and then ranking yourself, just like I showed you in the previous section, we're going to use Statcrunch here. We're going to put everything in Statcrunch and we're going to let it come up with the ranks. Because what we're going to need for the test statistic is going to be the sum of the ranks for each sample. And that's going to be these values that you're seeing here, R1, R2, R3, R4, for however many different samples or groups you have to compare. Now, other values that you're going to need to calculate your test statistic, lowercase n is just going to be the size of each sample. Capital N is your total number of values. So this is going to be the sum of all the sample sizes. And then K represents the number of samples that you have to compare. So using all of that information, we're going to calculate what's denoted as a value of H, and that will be the test statistic for the Kruskal-Wallis test. Now, as far as rejection region and critical value, this will actually be done using a chi-square distribution, and this is another distribution that we have seen before. When you run the Kruskal-Wallis test, you will always run it as a right-tailed test, and we'll talk about why a little bit later. But this is good because when you go to the chi-squared table, you do need to always make sure that what you have is an area to the right. And then chi-squared does have degrees of freedom associated with it. And for this test, that will always be k minus 1, where remember k is the number of samples that you have to compare. All right, so here's our basic steps. Of course, we start with the initial setup. As I said, we'll use the chi-square distribution, run this as a right-tailed test, find our critical value and rejection region. We will look at the ranks of the data. So again here, we're not going to do all of this by hand. We're just going to go to Statcrunch, get the ranks for the data, and then pull all that information together using the formula to calculate the test statistic. And then this is a traditional decision rule. If you're in the rejection region, you reject. If you're not, you fail to reject. All right, so let's walk through an example here. First thing is to look at how do we know to use the Kruskal-Wallis test. All right, so if I look at the information I've got here, I'm looking at the amount of caffeine in 16-ounce servings for a random sample of beverages. So what I want to note here is that I am comparing 4 different types of drinks. So I am comparing 4 groups, right? 4 pieces of information, and anytime I'm comparing 3 or more using a non-parametric test, I'm going to do this with the Kruskal-Wallis test. Now, as far as the initial setup, again, the null hypothesis will state there is no difference in the amount of caffeine. The alternative will state that there is a difference present. And we are asked to test the claim that the amounts of caffeine is different for the 4 groups. So that means we are looking at a claim here that falls in the alternative hypothesis, which is why we'll be looking to support that claim when we get to the end. All right, now what I'm going to do from here is I'm going to use the chi-square distribution to come up with my rejection region and my critical value. So I'm going to sketch out my chi-squared curve here. Now the chi-squared distribution is always skewed to the right, so I'm going to sketch out a little skewed curve here. And as I said, this will always be run as a right-tail test. So I'm going to shade my rejection region right over here in the right tail of the curve. Now, I'm going to need my level of significance. So I'm going to look back here and see that I'm running this test with a level of significance at 0.01. That will be the area of my shaded rejection region. And remember, my degrees of freedom are k minus 1. Now, k is the number of groups that I'm looking to compare. Okay, so right up here when I see that I'm comparing 4 groups, that gives me the value of k. So comparing 4 groups here means I'm going to have degrees of freedom, 1 less than that, which is 3. All right, now you guys know how to use your chi-square distribution table already, but just in case you need a little refresher, I'm going to pull up my chi-square table. I'm going to go to a level of significance at 0.01. And I'm going to go to 3 degrees of freedom. Now that's going to give me a critical value of 11.345. All right, so I've shaded my rejection region. This value that I found right here in my table is my critical value. And now I'm ready to get the test statistic for this Kruskal-Wallis test. Now, this is where I'm going to need to rank the data. And again, I showed you guys in the previous section how you could go into Statcrunch and get it to rank your data for you. And so that's exactly what you're seeing here. Because I needed to rank all of the data, I just copy and pasted each one of my 4 groups into this one column. And then, just so I could keep track of it for myself, I did a second column where I denoted C was all the coffees, S was the soft drinks, E was the energy drinks, and T was, of course, the teas. Now, I went in and I had Statcrunch come up with the ranks, because this is what I'm going to need right here to calculate my test statistic. And more specifically, what I'm going to need is the sum of the ranks for each individual sample. So my first sample here looks at the coffees, which means I want to take all the ranks for the coffees, just that first group. I want to calculate the sum, and that sum is going to be my value of R1. And in this case, that comes up to a sum of 105. Now, I need to do that for each group. So now I'm going to look at my soft drinks. I'm going to do the same thing. I'm going to take the sum of their ranks. That's going to be my R2. And the sum of my ranks here is 56. Now I've got two more groups. So I'm going to take my energy drinks here. I'm going to calculate the sum. That's going to be my R3. And this sum is 104. And then finally, I'm going to take the sum for the teas. That's going to be my R4. And that sum has a value of 35. Now, the other things that I'm going to need as far as calculating my test statistic here, I'm going to need the size of each sample. So N1 has a size of 5. N2 has a size of 7. N3 has a size of 6, as does N4. Now, that means capital N, which is the total number of values, will be the sum for all of my sample sizes, which here is a value of 24. Okay, so now I have everything that I need to calculate my test statistic. You can refer back to the formula that was defined towards the beginning of the section. But what this formula will always do, it will start with a value of 12. That is part of the formula. We will divide that by capital N, total number of values was 24, times N plus 1. So in this case, 24 times 25. And make sure you put that in parentheses so that both are divided. Now, next I'm going to have a big term in parentheses. And what I'm going to do for this term, for each group, I'm going to take the sum of the ranks squared, and I'm going to divide that by the size of the sample. So again, the sum of my first ranks was 105, and the size of my sample was 5. Now I'm going to go to my second group. The sum of the ranks there is 56. I'm going to square it, and I'm going to divide by the size of that sample, which was 7. My third group, the sum of the ranks was 104. I'm going to square that, divide by the size of that sample, which is 6. And then finally, the sum of the ranks for my last group was 35, so I'm going to square that and divide by the size of that sample. And then you don't want to forget, there's always going to be this term at the end that has to be subtracted, and that term will always be 3 times N plus 1, which again in this case is 25. Now, you can enter this all into your calculator in one step as long as you put parentheses in the spots that I've got parentheses listed here. All right, or you can work it out in steps if that's going to be a little bit easier. All right, but what I'm going to end up with here for my test statistic is a value of 18.197. Now again, what I'm looking for, normal rejection rule, is if this is in the shaded region. And in this case it is, right? 18.197, that is greater than the critical value of 11.345. What's important here is that it is in the rejection region. So we will reject the null hypothesis, and that will tell me if I reject the null hypothesis, there is enough evidence to support the claim, because remember our claim was that there was a difference in the mean caffeine content for these 4 different types of drinks. Okay, so at that point again, I'm testing for a difference between the 4 types of drinks. I get a chi-squared rejection region. I calculate my test statistic using the sum of the ranks for each sample. This was in the rejection region, so I rejected the null and in turn supported the claim. All right, now, one really big benefit to this test over the ones that we looked at in the previous sections for our non-parametric test is you do actually have access to the Koalas test in Statcrunch as a whole. So you can either use it to double check your test statistic, or for large data sets you could actually use it to do the whole thing. So just to compare here and to show you that I would get the same thing, if I am in Statcrunch, and you'll notice here I've just loaded my data as it is, each individual sample. I can go to Stat, go to my non-parametric test, and you'll see there that we have access to the Koalas. Now all I have to do here is specify the samples that I want to compare. All right, we want to compare these 4 groups, so I'm going to select all 4. I don't need to worry about anything else. I'm just going to hit compute, and then you should notice your chi-square value here is 18.197. It also gives you access to the p-value, which is another way that you could make the decision in your hypothesis test. All right, now, just to give you one more example, and I went ahead and worked through this one. But again, anytime I want to compare 3 or more groups, this is the test that I'm going to use. So again, null hypothesis, there is no difference in the salaries for these 3 groups. Alternative, there is a difference. Chi-squared rejection region. We had 3 samples here, so degrees of freedom is 2. I went to Statcrunch. Now to calculate this using the formula, I ranked all of the data. I took the sum of the ranks for each individual sample, and then I plugged everything in to my formula for H. That gave me a test statistic of 0.433. That was definitely not in my shaded region. It's much less than 5.991. So in this case, I failed to reject the null hypothesis, which tells me there is not enough evidence to support the claim that there is a difference between these 3 groups.